Now, my objective wasn't to show you how awesome I am at Gaussian elimination for 3x3s, especially with simple math like this. And you can see, by the way, I picked this problem right, so it works out so nice. I just get ones everywhere. And, okay, I like that. But let's do the following. I really want to know how much effort did it take to do this. And this is what this is all about. Now, ax equal to b is going to be one of the fundamental problems you're going to solve. So, in fact, in this class, for your homework 4, you're going to do 5 different ways to do ax equal to b. Okay? And then you can say, well, they're all going to give you the same answer, right? You're just solving the same set of equations. You're going to get the same answer for each. So the only thing you care about, actually, in this class for computing is how fast can I do ax equal to b. Okay? Part of getting the right answer from a computational viewpoint now relates to how fast can you do it. Okay? If you do it the slowest way, yeah, you got the right answer, but you did it wrong. Okay? This is about speed. Everything's going to be about speed here. This is often going to be the biggest problem for you. Do you know why MATLAB was invented? You know what MATLAB even stands for? Matrix Laboratory, right? So it was all about ax equal to b. The guy who started this, Cleve Muller, he cared a lot about ax equal to b. And ever since then, people have cared a lot about ax, because that's the big holdup in most codes. Okay, so let's count operations. So what did I do in this Gaussian elimination algorithm? I started with a pivot. And what I did was I said, I got to go to each row below that and try to make some zeros. So I got to go to each row. And for each row, I've then got to walk across all of it. So for here, I say, okay, I got to go here, figure out what this is. And then I've got to manipulate 1, 2, all the way across that row. Right? So for each pivot, I would say, I've got to go down. How many of these do I have to go down? Well, here's a 3 by 3. But in general, there's n of them. I've got to go down n. So if I have an n by n system, I have to think about going down. Okay, I'm going to go down these n rows. For each row I go through, I'm going to have to do n manipulations this way. Because I've got to go change this number, and this number, and this number, and this number, all the way across. Okay? So this is what I did here. The first step was to say, go to this row, go across. Go to this row, go across. I've already done, in this first step, n squared operations just to do this. Okay? Then I go to the next pivot. And then I got to go down the rows, across the columns. Then I go to the next pivot, down the rows, across the columns. So when you walk down that diagonal, there's n of them as well. Overall, then, to get this solution here, I had to do something like order n cubed. Now, there's some factors in there. You know, okay, the second time, you only have to do n minus 1 of these things instead of n, and then you, fine. There's some factor. Who cares? The point is, this is the ballpark figure for you. Okay? So, you have yourself a 10,000 by 10,000 matrix. 10 to the 5 is the size of that thing, and it's going to cost you to 10 to the 15 operations. Okay? So, it's non-trivial. Normal time when we put in, backslash works fine if you're working with matrices that are not that big. Right? Just hit return faster than you can get your hands back on the keyboard. You got the answer. Okay? But we're not solving about problems like that. We're talking about huge problems. When you have 10,000 by 10,000 matrices or bigger, you hit that backslash button. Okay? It's going to say, oh, I got to do whatever the size of that thing is. I got to do n cubed operations. And that's going to cost you. So this is your price. Okay? Computational cost. And this is expensive. In some sense, this sets the upper bound. This is the most you should ever pay for doing this operation. N cubed. Okay? What is the theoretically fastest thing you could ever do? You have n things you try to determine, right? You're trying to get an answer that has n. So the best you could ever potentially do is order n. That's if like you knew the answer. You could just update the answers, right? So somewhere between here and here is what you're trying to look at is this is the most expensive you could ever pay. This is the best you could ever do. Okay? So you want to think about what lives in that space and how do I generate methods that can do that. I'm going to give you a little precursor to things here. The most dependable and probably the most standard thing is if you can get this, it's awesome. N log n. Keep that in your head. If you get an n log n scheme, you rock. If you can beat n log n, job anywhere you want. Any top university. You'll win prize after prize because you rock even harder if you could beat n log n. Okay? People are trying to always do this, but this is really hard to beat n log n. Okay? So there's a little challenge for you for like homework 5. Beat n log n. Okay. Okay. And we'll talk about that in a minute, but we're going to talk about a more systematic way to do things. By the way, sometimes you can beat some of these things if you assume a lot of structure about the matrices and so forth. But generically what we want to do is say, you give me some generic matrix A. I have no properties with it. Just it's a matrix. Nothing special about it. No symmetries. No this or that or the other. You have to figure out a way to solve it. Okay. So is everybody okay with this? So the whole reason for the example is simply the idea of conveying to you that there's operation count. Gaussian elimination is order n cubed. And, by the way, never told to you before, that is the most expensive way to solve that problem. Okay? It's like paying full price when there's a sale somewhere else. Okay. So let's go back and let's think about different ways to consider this problem. And what I'm going to talk to you about today is probably the most standard way to do this problem. And it's called LU decomposition. Okay. Here's the idea behind LU. You're going to say, what if I could write my matrix A as two matrices, L and U? That's the name, LU decomposition. What's special about L and U? What we want to do with L and U is to say that L is some matrix that looks like this. Oh, sorry. So the L matrix is lower triangular. Lower triangular, that's the L. And what do you think the U is going to stand for? Upper. Yeah. Okay, so here's what it looks like. And this pen is quite strong today. So it's kind of like an upper or something. I don't know what it is, but it's like, whew. When you get fresh pens up here, it's like, wow. Okay, so big deal. What if we can do this to a matrix? What if this matrix has this LU decomposition? Here's the big deal about it. Let's assume A now has this LU decomposition. So I have L, U, X is equal to B. Now here's what I'm going to do. I'm going to call this U times X Y. Okay, so it's Ux is equal to Y. And what's left over is Ly is equal to B. So I seem to have gone backwards. I took my problem, which is Ax equal to B, and I broke it up into two problems, which are Ax equal to B's. But here's the structure of this. You know what Y is, you know what X is. But right here, you could solve for Y. Right? You have B, you have L. Let's suppose you have L. Then I could solve for Y. Okay, well, so how do we solve for Y? Well, you might Gaussian eliminate. But notice, Y is in what form? It is lower triangular. Let's do a 3 by 3 example, right? So here's would be my system. But notice, I already have this in lower triangular form, so I can just basically do what's called forward substitution. Because the first equation says y1 plus 0y2 plus 0y3 is equal to b1. So the first equation comes out to be fairly simple, which is y1 is equal to b1. Great, I got that. Second equation says m21 y1 plus y2 is equal to b2. Notice I already have y1. I know what m21 is. So I can get y2 from substitution, which is y2 is equal to b2 minus m21 y2. Okay? Oh, sorry, y1. And y3 then basically is b3 minus m31 y1 minus m32 y2. There we go. All I had to do, I didn't have to do any elimination. I just substitute. How much does substitution cost me? Because it's still an algorithm. I still have to do some work here. But I don't have to do any elimination. What it costs me is, let's take a look at this. I've got to first solve for y1. So what I've got to do substitution is I've got to walk through every single row. And there are n of them. Okay, so there's n amount of work going down like this. And for every row I do, I've got to solve one of these equations, which is solve for y2 in terms of everything else that's there. And there's n of these. So n of those. So a substitution routine would cost me order n squared. Not bad.